Hello, we're doing a short video clip on static equilibrium here, and we're going to explore how the net forces sum to zero and the net torque sum to zero in some static equilibrium cases. We will do a do-it-yourself experiment where we can explore these conditions in further detail and set up the equations of motion to look for unknown masses or unknown force values. All right, so number one thing to understand is the net forces must sum to zero and the net torques must sum to zero, just as you see here as I'm balancing this little meter stick. And also my little balancing guy right here. Okay, all my up and down forces sum to zero, and all my torques, my forces off center mass, will sum to zero. The moment I have a net torque that's not zero, we begin some sort of rotational motion, and it's no longer in static equilibrium. Okay, so we could see many cases where static equilibrium can be displayed, and we could analyze these. Bridges are great cases of static equilibrium where all your forces and torques sum to zero. So here's a bridge at the Hoover Dam. And if we look at all the supports and all the upward forces from the support, they will be balanced by the downward weight force of gravity. Okay, and then what we really want to remember is the two conditions: translational equilibrium. So when something's translating, all the points of mass are moving with the same velocity. Translational equilibrium conditions mean that the sum of forces, which is proportional to the acceleration, must sum to zero. And equilibrium just means, you could move with constant velocity or you could be at rest. When we put the word static in front of it, it means it has to be at rest. And the conditions for rotational equilibrium is that all the net torques, which is proportional to the angular acceleration of the object, must sum to zero. And you want to remember what your torques are. Torque is the vector cross product of your position vector with your force vector. So it's a force applied off center mass with respect to a defined axis of rotation. So whenever you're doing these equilibrium problems, when you're combining both forces, translational forces, and torques, you must define the axis of rotation to do the analysis. Now, one thing is really important to remember is that you could have translational equilibrium, but not rotational equilibrium, or vice versa. Okay, so you could have, I have a little video display coming up in a bit with a wheel where you could see how that is demonstrated. You could spin a wheel. I could apply some acceleration to it, and I could say, as long as my velocity is not constant, I could say, this is an example of my torques not summing to zero, but my translational values, but the sum of my forces is equal to zero. Okay, so let's put a stop to it, slow it down. So there again is an example where my torques don't sum to zero, but my forces do. Now what if I had a skidding wheel? So let's skid this wheel. In that case, if I can slow it down or speed it up, then my sum of forces is not equal to zero, but the sum of my torques is equal to zero. So that's the case where I only have my translational forces not equal to zero, but my torques are. So that's a big difference. So translational is when all the points, the center of mass points, stay constant. All the masses move with the same velocity and they have a constant distance between them. And what happens with the other situation is rotational motion means all the masses at different spots, at different positions from the center, will rotate with the same speed, but will have a different amount of torque applied to them. So there's a lot involved in looking at torque. Okay, so diving boards are great examples of equilibrium. What we have here is we have the weight of the diver going down. Okay, we also have, let's say, the center of gravity of the diving board is through the center, so we have the weight of the diving board also going down. So we have weight here, weight of the diver, weight of D, and this is the weight of the board. Now these downward forces must be balanced by upward forces. So what we can do here is that we have upward support forces, normal forces pointing upwards. And these downward forces are balanced by these upward forces. So this arrow, these vector arrows will match the downward vector arrows. So our net forces should sum to 0, but also our torque. So wherever we define the center of axis of rotation, we'll look at all the torque. So just the weight of this diver alone will make it go in this counterclockwise fashion, and that would be a positive torque. And then this upward normal force by the support will also make it go in that fashion. And then we have some other supports over here which would make it go in the opposite direction, so that all our torques would sum to 0. So we get torques from all these forces. So the most important thing is to identify all the forces acting on the body, in this case the diving board, and then sum the forces and sum the torques and make those sums equal to 0 to analyze the problem. Okay, so seesaws are great examples as well of forces balanced out and torques balanced out. So you can see the weight of the people will be balanced by the positions they're on. So we have the weight of this person, and then we have the weight of this larger person here, and then we have the normal forces of the supports pointing upward here. Okay. So we identify all the forces acting on this board, and we also have the weight of the board through the center. Okay, so we have 3 weights: the weight of the board, the weight of the 2 masses of the bodies, and then we have the normal force, the pivot points pointing upward. And we would look at all the net force, sum the net force to 0, and sum the net torque to 0 in that case as well. So seesaws, what we know is we balance out our mass. So if you have a lighter mass, you will tend to go more outward from the axis of rotation, whereas if you have a heavier mass, you'll go more inward to balance out the lighter mass. And that's how you could get a seesaw in equilibrium. So really good examples of equilibrium conditions at work. Okay, and if you ever do handstands, you know it could be quite a feat trying to stay in static equilibrium. So it depends on your center of gravity. So if you assume the center of gravity of this little guy, my son, is going downward, that will be balanced by the hand forces pointing upward, the support of the hands. Okay, and a little bit of a wobble, and all of a sudden the system is no longer in equilibrium. Okay. And of course our bodies are always using and applying the equilibrium conditions. If you stick your hands out, you know, we have our muscles and our joints that are acting upward against the weight of gravity. Okay, so even if you pull a weight, if you have a weight in your hand and you're holding a weight, you're going to use your muscles to balance out that downward weight force. Okay, so what we're going to do now is we're going to look at a setup very similar to what we have drawn here. We're going to have a support, a board or a stick in this case, measured out to be 1 meter. And we're going to hang some masses, 3 masses from it. And we're going to suspend it from 2 strings that connect in the center. We're going to hang this up and we're going to create a system in static equilibrium. And we're going to analyze this system, and we can use it to find the mass of the stick or the unknown tension forces acting on the stick. All right, so coming up, we're going to do this do-it-yourself equilibrium problem. Look at suspending a stick a measured stick, such as a meter stick, and we're going to suspend a bunch of masses from it. So here we have our stick, and what I'm trying to do with this stick is make an equilateral triangle between the two strings and the parts at which they're attached. So this is not quite an equilateral triangle, but that's what I'm after. And in this little lab activity I wrote up, what you want to do is have 60 centimeters this way, 60 centimeters this way, and 60 centimeters this way. And it makes the geometry makes the problem a little easier to handle. So I'm going to do my symbol for equal distances here. And once I achieve that, I want to suspend a mass here, another mass here, which is not necessarily the same. And I could do that and balance it out, but I want to keep these two masses different to start with, and then add a third mass somewhere along here to balance the beam out and figure out what that mass needs to be or where I need to position it. Those are two things I could solve for in this case. So what I'm going to use for masses in this case is these hexagonal nuts, which I've weighed, which I found the mass of using my scale. So here I have one, the very heavy one, which is 50 grams. Actually, that's my so I'm going to measure this, and I found it to be about 50 grams. And then I have another one. Double checking, that's another 50 grams. And I have another mass, which is about 30 grams. And then I have another mass, which is 15 grams. Okay, so I'm going to go ahead and write those down, those numbers. So I have 50 and 30. And I have another one that's 25 grams. Now, ideally, it would be nice if you knew the mass of your stick. This one's 0.125 grams approximately, but it's not necessary. And the reason why is because if we choose the center of the meter stick, which is where we're going to assume the center of gravity is, so if we choose the center of meter stick as a point where the center of gravity is, the CG, then we could choose that as our axis of rotation, and we don't have to know that mass because it's not going to apply any torque. So what we want to do here in this activity is, as best we can, make our triangle. So I want to put this at, I want 30 centimeters here. I want to put this at the 20 centimeter mark, and I want to put this at the 80 centimeter mark. To make life a little easier, I am going to get a little tape, make things stick a little better. So I need to tape this here. All right. I should have brought my duct tape, an important necessity in the world of every day. And I'm going to take this side to the 80 centimeter mark. And I've measured these out previously because I think it would be very, not very exciting to watch me measure this. And I have my equilateral triangle. Okay, so next up, what I'm going to do is I'm going to suspend this. And I'm going to use a coat hanger. And I'm going to suspend this from my ceiling fan. Whoa. But first off, I need to retie this. So, an important factor. All right, now you have to watch me tie this for a second. All right, that could be called your coffee break. All right, okay, so I am going to hang this off my ceiling fan. You have to just use what you can use. And then what I see here is that I have, once it stops wiggling around a bit, I have forces in balance. So I have a force along this string right here, which is my tension force. And I could find the components when I measure the angles. And I have a force along this string, which is also a tension force. Now this tension force and this tension force should be equal because this is an equilateral triangle, right? So by being an equilateral triangle, same lengths, same angles, and you can measure it. You can get one of these paper protractors online, which is great, and measure these angles and verify that. Or at least do your measured values, your experimental measured values, because this always surely will have a little bit of error as you're making this, because the strings need to be readjusted, etc. So this should be approximately 60 degrees, approximately 60 degrees, and approximately 60 degrees this way. So what happens is I have 60 centimeters, 60 centimeters, 60 centimeters, and I could find my components of tension here. These are unknown if I know some of the rest of the problem. So this tension plus this tension equals that full tension at that pivot point. Now let me add some complications here. I have some pre-cut string loops. I'm going to take this heavier mass, which is, again, I'm just going to verify. I have some fishy measurements here. Yes, it says 50 grams. So I'm going to verify that it's 50 grams, and I'm going to tie it to one of these spots right here. And we're going to start looking at the downward forces of weight in this problem. Right now we have one weight, and that one weight, if we assume the center of gravity of the meter stick is through the center, again, assuming that all the particles are equally distributed and that the force of the gravity acts the same on all of these, it's going to be the same as if we see all these mg values of all these particles are the same as if it acts through the center. So we're going to say we have the weight of the meter stick going down, tension up, tension up. So what we have is our translational forces, our upward forces, are balanced by our downward forces. And of course, this sideways force, this tension component this way is balanced by this tension component that way. So that is our translational force equation. And if I add a piece right here, I'm going to send this in not equilibrium mode. Okay. So this might be a tricky little exercise to do. You'll probably have to do some different hanging maneuvers so everything doesn't collapse on you, and so on. All right. I guess that's okay. So now I'm having this hang this way. So notice that now I have more downward force pointing this way, and that's trying to create a torque. Okay, so it's going to try to make it spin in this case, it's going to be in this counter, no, this is clockwise, in this clockwise direction. Okay, so this tension alone is pulling it in the counterclockwise direction. This is pulling it in the clockwise direction. So we also have a torque created here because this is pulling it in this clockwise direction. So when it's in equilibrium, we'll have this torque and this torque and this torque, and the torque of the mass of the meter stick, the force, the torque via the weight of the meter stick is also acting on it, but the sum of my torque should also be 0. So I have that getting tilted a little bit. So what I'm going to do is balance this out by adding some other forces. I'm going to tie another hexagonal nut on here. So I probably should have had these pre-made, but this is a good moment to take a coffee break. As you can see, I've got my 3 masses balanced on my stick. Okay, so what we have here is we have a system in static equilibrium. There's a little wobblies, but we won't include that. It's pretty static. And we have our forces again. We have tension up this way. We have tension up this way. We have the stick, which has mass, so it has gravity. Gravity is pulling it downward through its center of gravity, which is right here. We're going to, all the mg's, all the little particles inside this stick, all feel acceleration due to gravity. So they each have a weight. So if we look at the averages of all those, it's the same as all those mg's are the same as all the mass times the acceleration due to gravity acting through the center. So that's how that works. Now we have a weight here. We have the highest mass nut suspended. It has weight, so it is pulling on the stick this way. We have the nut here. It's pulling on the stick, so it has mass, so it's pulling this way. And so does this one. This also has a weight. So what we have is we have several forces. So if we look at our translational forces, we have upward forces, this force, this upward force, this downward force, this downward force, this downward force, and this downward force, all sum to 0. So the sum of our translational y force is sum to 0. But we also have the x component of our force, and this way, and the x component of our force, which is from tension, acting this way, and these two cancel each other out. So that sums to 0. So we have translational static equilibrium. Now next we have to look at our torques. Now the center, if I choose my central axis being right at the 50 centimeter mark, that's my axis rotation, I want to go ahead and measure my R values with respect to that center. I want to measure my R values at which the forces act. So I have a force acting at this position, which is 30 centimeters from the axis rotation. I have a force acting in that direction at an angle of 60 degrees here. I have a force acting this way at, again, 30 centimeters. And I have this force placed an extra few centimeters. So it'll be about 30. I'm going to come around here and just double check. This is an extra 5 centimeters. So this force is acting at an R value of 35 centimeters from the axis rotation. So it's going to pull it downward this way. It's pulling down, so it results in a counterclockwise motion. This mass is pulling down, so it will result in a counterclockwise motion. This tension is pulling it up, so this will result in a clockwise motion. And this tension is acting at 30 centimeters from the axis of rotation. So that produces a torque that would make it rotate in this counterclockwise direction. And this mass is producing a force of gravity on it. So it has a force acting at it at 30 centimeters, which would result in a counterclockwise motion. So those are our torques. Now there's also the torque from the central, the mass of the meter stick, but since it's at the axis of rotation, the R value is 0, we don't have to include that. So if we sum this torque, this torque, this torque, this torque, and that torque, we should get 0. Okay, let's look at the static equilibrium do-it-yourself setup and see how the equations work out and how we could use this apparatus that we put together to find unknown masses, unknown tensions in the strings, the unknown mass of a meter stick or the stick that we're using. Okay, so let's do the setup here. Now, to start with, make sure that your setup is again very similar to the pre-lab diagram. And what we're doing here is we're taking a stick that's measured out to be a meter stick and we're suspending 3 masses from it. So first I'm going to start off with just a general diagram of this static equilibrium setup where all the forces and torques sum to 0. Okay, so what we have here is we have an equilateral triangle as best as we have put together. Made by the strings attached to the stick. So here's our stick measured to be a meter, or if you do happen to have a meter stick, the meter stick that you use. Okay, and we have our mass 1 here suspended, 20 centimeters in. So this is the 20 centimeter mark. So here's the halfway point of the meter stick. So this would be 30 centimeters this way and 20 centimeters this way. Okay, and what we're doing here is we're suspending 2 other masses in different parts on the left-hand side or on the other side opposite to the M1 side from the center, and we're suspending these other 2 masses in a way that produces a static equilibrium setup as shown in the previous video clip. Okay, so we have M2 and M3 and we're adjusting these at different positions. So we want to mark what these positions are because these positions will be very important in finding our torques that they produce. Okay, so we have 3 masses suspended from this meter stick, and of course we cannot discount the mass of the meter stick itself or the mass of the stick itself, and we're going to assume that its center of gravity is the center of mass, and if we condense all this, it will act as if the entire weight will be acting in the center of the meter stick. Okay, so we're going to assume that the center of the meter stick is where the center of mass and the center of gravity is. So we'll say this is the mass of the meter stick in the center. Okay, MS. And again, this is suspended by 2 strings or cords. And we could call this, I'm going to go along with the diagram setup I have. We'll call this T1 and T2 because we know that this is the force of tension acting along the string, and this is another force of tension acting along this string, and we have this connected at some point and we're hanging this whole apparatus up. So what I'm showing here is just a general diagram of all that's acting on it, and we'll see that we have tension forces acting on it, and through these masses we'll have weight of 3, weight produced from mass 2, the weight produced from the meter stick, and we'll have the weight produced from mass 1. Okay, and what we're trying to do here is we're fixing these strings at the 20 centimeter mark as closely as possible, 20 centimeters from each edge. So we know that this right here is 30 centimeters from the center. And the other thing we're trying to achieve here is an equilateral triangle. So all these angles are approximately 60 degrees, and you could write down the exact angles by measuring those with a protractor. Okay, so what we're here, some assumptions that we're making and what we're trying to produce in this apparatus equilibrium setup is that we want theta 1 to approximately equal theta 2 to approximately equal theta 3, and we want these as close to 60 degrees as possible, making an equilateral triangle where all interior angles add up to 180 degrees. The other thing we want to achieve, but we're going to compute experimentally, is the tension 1. We want to be approximately equal to the tension produced by fixing at the second position. So here's our first tension, our second tension, and I'm using capital T, but again, you would use FT as your symbol for your tension. Okay, so those are two important ideas. And the other thing we want for an equilateral triangle, we know all these lengths are the same. So these lengths should each be about 60 centimeters. So this is L1, this is L2 as it goes all the way down, and this is L3. Okay, again, this is my general diagram. We want L1 to approximately equal L2 to approximately equal L3, and all these are about 60 centimeters. Okay. So this is our setup. This is what it looks like if we're doing an ideal diagram of that apparatus setup. And what we want to get here is we want to set up the equations of motion, okay, to produce and apply our static equilibrium conditions to find where these positions need to be, or what these unknown masses are, or what the tensions are in the string, like our lab. So we will experimentally have our masses. I use hexagonal nuts, and they tend to go between 3 grams and 30 grams, depending on the size and the finish on these. So if I assume that my mass 1 is approximately equal to M, my second mass approximately equal to M3, and let's say that these are 4 grams. These are hexagonal nuts. I used to hang from these positions, except for this is the center mass of the meter stick, and my mass of my meter stick is approximately, I do have a number written down, these typically are 125 grams. Okay, that's what we use a lot in our lab experiments. Okay, so we have those numbers, and those will allow us to find all these weights. Okay, so this will allow us to find these tensions in these strings. So there's a lot here in this setup, a lot of information that will allow you to find the unknown tensions. And of course, we could go on and we could also apply these same techniques to finding unknown mass. So to start, that's just a general diagram. Now, if I do a free body diagram, and we use to get the equations to help solve for T1 and T2. Okay, my free body diagram in this case, it's gonna be a little tricky. I'm gonna condense my meter stick into just a little bit of mass right there. And what I have here is I have the weight total, which equals weight 1 plus weight 2 plus weight 3 from the 3 individual masses of the nuts, plus the weight of the meter stick upward. And those are all vertically down. My convention is going to be up positive, down negative, positive to the right. And then I have two tensions acting on it. So I have T1, and I have T2. So that's my free body diagram. And I'm going to use that first and equate it to the techniques I know from previous equilibrium problems with just the forces and not the torques. So my equations of motion, okay, so these would be my force equations, my translational equations. From my translational forces, I will have the sum of all my forces in the vertical direction equal MAY, and that needs to be 0 to be in equilibrium, which is what we're trying to achieve here. And we know that this would be my Y forces here, so I'd have T1Y will equal T1 times sine, and the angle here, my diagram's a little off, but this angle right here should be 60 degrees. Okay, so here, the Y component of tension will just be T1 sine 60, and then T2Y would be the same way. That would be T2 sine 60. Now the X components would be just the cosine of those angles. Okay. Because what we have here, when we make our triangle, this is the opposite angle. So that's T1Y, and that's T1X. And you have a similar setup on this side as well. Okay. So if I look at my vertical forces, I'm going to say, well, I'll have T1Y plus T2Y minus the weight total, which I could get a number from, knowing these masses, should equal 0. Okay. So what I have is essentially T1 sine 60 plus T2 sine 60 degrees equals M total times G. So here's one equation I can use in helping me find unknown tension. Now the next one I have is the sum of all my horizontal forces equals MAX, and that should be 0. So in this case, the only contributions I have in my setup to the translational motion in the horizontal direction will be the X component of this tension and the X component of this tension. These are all vertical. The weights are all vertical. So in this case, I'll have the right side is positive. So I'll say, when I look at this will give me a better indication for my general diagram. So T1X is pulling in this direction. So I'll have T1X minus T2X equals 0. So what I have here is T1 sine 60 cosine, excuse me, minus T2 cosine 60. Okay. And that should equal 0. So I get this nice equation. I could get T1 in terms of T2. I could say T1 equals T2, and I'll have cosine 60 degrees divided by cosine 60 degrees. So we can see that these should be equal. which we assume also in the setup. So we know that T1 equals T2, and we get to say that's T. Okay, so that one doesn't offer that much help in as far as finding what the general value is, but we do know that these now are equal, so what we should have here is we could break this one down further and say 2T sine 60 equals M total G. Okay. Approximately. Now, how do we also apply our torques? And let's say we didn't know what the mass of the actual stick, right? It might not be given to you, and you might have to find it. So that would make this part unknown here in this equation, and we could use what we know from our torque setup to find that as well. So here's one equation, here's a second equation you have, okay. And let's see how we could get another equation using our knowledge of torques to set this up. So I'm going to do a torque diagram. So notice I do a general diagram, a free body diagram, and the torque diagram is a little different in that you show the points of contact. Okay, so here's my torque diagram, which I cannot emphasize enough the importance of doing torque diagram when you're doing rotational mechanics, when you have to include torques into your equations. So here's my torque diagram. And I'm going to make it really simple. I'm going to not show the width of my meter stick. And I'm going to show the forces at the points of contact. And the important thing here is to look at where the rotation, your axis of rotation is, define that. So I'm going to define that in the center of the meter stick. Okay, right at the 50 centimeter mark. That will make life easy. So I'm going to splice this right through the center. This will be my chosen axis of rotation. Okay, and again, I have these tension points at 20 centimeters from each side, 30 centimeters from the middle. So here, and going along with the same convention, I had defined this as T1. Which is approximately 60 degrees, and this is T2. Okay, so I show two forces. That should be as equilateral as you can get it, right? Not always easy. Okay, I have those. I have the weight of the stick or the meter stick going through the center, and that is really nice when it coincides with your chosen axis of rotation, because it's 0 distance from the center, which means we could cancel that out. So this will be the weight of the meter stick, and here at the 20 centimeter mark is where I have the weight of mass 1. Okay, so that's 30 centimeters from the center. And then I don't know what these values are. These are experimentally done, but I have weight from mass 2. I hung another hexagonal nut, and they don't all have to be the same masses. You could experiment with different masses. And let's say I put a third mass here at this distance so that I have the entire system in static equilibrium, no motion whatsoever. Okay, equilibrium, you can have constant velocity, but static equilibrium must be at rest. Those are those conditions. Okay, so here's my torque diagram. Now, what I'm going to apply is the equilibrium conditions to get my my torque, rotational equations. And there's going to be a lot here. Okay. So what's going to come into play is our definition of torque and how it relates to force, and the offset, how far away from the center it is, the axis rotation it is. Okay, so what we have is we're going to use the sum of all our torques we know is equal to R cross F. I like to do vector cross products to get them exact, but you have all these other methods to use, your lever arm method, etc. But the idea is you take the perpendicular component of its distance from the axis of rotation and times it by your force, or you take the perpendicular component of force and multiply by R, or the way we can define our torque, R cross F, RF sine theta, R perpendicular F, or RF perpendicular. Okay, so this is probably the easiest we could do here from our setup. We have a lot of perpendicular components for weight, which makes it easy. The only ones we have to worry about as far as angles go are our tension forces. So now my convention is if the force I apply causes a counterclockwise motion, it will be a positive torque. If the force I apply on the object produces a counterclockwise motion, I will have a negative sign. So I want to look at each individual force, like T2 will make it rotate in this direction if it was acting alone. So T2 would make it go in a counterclockwise direction, so it would be positive. Whereas the weight from mass 1 will produce a torque that will make it rotate in a clockwise fashion, and that will be negative. So I'm going to start with T2. So each one of these forces produces a torque on the meter stick, okay? So it's important I know the distance from the axis of rotation and the force. So let's start with this one first. Okay, so I'll start with this torque first. So really what we need is we're going to know that the torque from the second tension, and that's going to be positive, minus the torque produced by the weight of mass 1. Okay, that's going to be clockwise, that'll be negative. This is 0, so this torque is 0, so I don't even need to include that. Okay, that will not make it rotate counterclockwise or clockwise at all. And then I move on here, the weight from mass 2 would produce a counterclockwise motion, so I would say plus the torque from weight of mass 2. And then the weight of mass 3 would also cause a counterclockwise motion. So I'd say plus the torque caused by the weight of mass 3. Okay. And then finally, the last force that we need to account the torque for is T1, and that would produce a clockwise motion in that direction. So we'll say minus the torque due to T1, this should all sum up to 0. Now we add in the details, okay? And we'll get another equation we could use to help us solve for the unknowns involved in any of the questions that are posed in this problem. Okay, the torque from the second tension would be, what we have is it's applied 30 centimeters from the axis of rotation, so that would be 0.3 times the second tension, T2, which we don't know. Okay, it's RF, but it's applied at an angle of 60 degrees, so we want the perpendicular component, so we want 0.3, the magnitude of that tension value times the sine of 60. So that's that torque right here, minus the torque of weight 1. So this is applied at 0.3 as well, from the center times the weight caused by mass 1, so that would just be whatever mass 1 is times g. Okay. Plus the torque produced by the weight of mass 2, so that'll be minus. And this one we don't know. We're trying to adjust this. So you're going to experimentally get that value, right? You're going to place it place these two masses at different distances that would balance this out. So I'm going to say R2 M2G here, and we can fill in those values. And then we have the torque produced by the weight of mass 3. So here we're going to have plus, and my bad right here, that's minus M1 plus M2G. So I have to abide by the signs, and I say plus, same thing for mass 3 is going to be R3, whatever the experimental distance I have is, times the mass of 3 times little g, and finally minus the torque produced by this tension force right here. Okay, so here I'm going to put in 0.3 because that's going to be the distance that this is applied. It might not look equidistant in my diagram, but that's what the lab has you set it up as. Okay, so minus 0.3, and now we have T1, and again the perpendicular component is what we're looking at for this force applied at this position. So T1, and then we have sine 60. And I should say R is position. That's a more accurate way of saying it. And all of that will equal 0. So here we have another equation, right? So you have this equation, and you have this equation here. This is number 3. You could clean it up some. You could clean this up and you could see how you could get some. These are going to be equal by that statement right there, and you could see how we could solve by knowing these values experimentally, how we could solve for T1. Okay, so you fill in all these other values. So this is number 3. So we use 3, 2, and equation 1 to solve for our unknown. So given what you have, or what you experimentally find, okay, and you can verify that. So, like in this case, you don't have the total mass because you don't have the meter stick. But here, that cancels out by the torque diagram, so you could find your tension value, and when you find your tension value, you could plug it in here, and you could find the mass of the meter stick. Okay, that's another unknown to do. So, that's how you do the equation solving and the associations to the do-it-yourself equilibrium setup. All right. Hello, physics aficionados. Here we are with my lab assistants, Dr. Seth and Dr. Yulee.
And Dr. Kuiper.
And Dr. Kuiper. And we're doing demonstrations on what subject?
Equilibrium.
Yes, even more so, we're going to do static equilibrium. That's when you're supposed to be at rest. Now, here we have a makeshift seesaw, and what we're trying to do here is balance the masses of Seth and Ulysses. All right, so Ulysses and Seth, can you tell me your approximate masses here?
70 pounds.
70 kilograms?
Pounds.
Around 50 pounds.
Around 50 pounds. So we have to do our conversion to kilograms. But we know what we're seeing with the pounds is that Ulysses has more weight than Seth. So if Ulysses has more weight, what do we need to do to balance this seesaw? Balance the mass of your weight on the seesaw.
Then I would have to go closer.
Oh, here's
You'd have to go closer.
Dr. Sky.
And Dr. Sky, yes. And Seth, what would you have to do? Since you have less weight acting on you by the force of gravity, what would you have to do?
I would need to move backwards.
Okay.
Or lean backwards.
Okay, so, okay. Thank you for watching, physics folks. With me are the call boys closing up our segment on static equilibrium. And they are taking a bow for us to keep things in static equilibrium. Let's see your bouncing bird bow. Yay! Good job! How long can you hold it? How long can you stay static?
Forever. Okay, that's good.
Good job, guys! All right, thank you so much. Bye.